All right, we're back. We're going to be on page 4 of notes 13 of Calc C, Euler's method stuff. But I realized that in my excitement to have finished that last problem, I didn't actually finish that last problem. I was supposed to find the specific value of C. So like if we go back to the previous page, like all over the place here, we knew the initial condition was 0, 1. And we actually solved it, and we got this as our approximation was like 7.125, I think. And now, like, do we know that it's going to be an underestimate? I don't know that we necessarily know that yet. We'd have to find the second derivative and look and see if concavity is positive or negative. But we solved this. We use the initial condition. I get that C is 2. So really, this is the equation. And then y of 2 is 11.778. So we got an underestimate. We're not at the point where we necessarily want to look too deeply into that. Although, I mean, I kind of do. So like if let's see if we can do this. So if dy dx, maybe I'll use a different color. This was not the plan, but you know, duty calls. We got to do this. So dy dx is x plus y. So then the second derivative is going to be 1 plus dy dx, which, you know, okay. And then we'll sub in, right? Because we know dy dx is x plus y, so we get 1 plus x plus y. All right, so what happens here? So if the solution curve is going to be concave up, it's going to be so if concave up, then the second derivative has to be greater than 0, which means that 1 plus x plus y is greater than 0, which means y is greater than negative x minus 1. So as long as our solution curve is above negative x minus 1, which if you remember is actually the slant asymptote of this thing, as long as we're above that, the curve will be concave up, which means we'll get an underestimate. So how do we know that we are above that? Well, our initial condition, do we know we're above that? I don't know if we know we're above that. So dy dx is x plus y. I think we do know that. Here's why I think we do know that. So this is actually a complicated thing. So we're given 0, 1, and we are approximating y of 2, right? So we know that x is definitely greater than 0. And then we also know, I mean, we just know that x is greater than 0. So if x is greater than 0, how are we guaranteed that we're above negative x minus 1? So x is 0, y is 1 already, and then x is going to increase, so x is positive. And then is like, do we just know that y is positive for some reason? I mean, it's 1, and then dy dx is x plus y, so you start out increasing and just keep getting bigger values. So yeah, I'm going to say, I think we do know that x is greater than 0 and dy dx is greater than 0. I've convinced myself that that is definitely true. So x is 0, and then y is increasing from 1. So you're going to 2. So I do think that, what am I even saying? Well, y is positive and negative x minus 1 is negative. So yes. Y is greater than 0, negative x minus 1 is less than 0. Therefore, the second derivative, I bet we're all glad that I went down this road. It's greater than 0, so yay. All right, concave up, therefore tangent lines are below, therefore you had to get an underestimate. That's what I wanted to say. Now, do I even want to do this? I mean, I said I was going to be on this page. Yeah, let's do, oh my God, slope, okay. Dy dx is 1 plus y. So I just add 1 to whatever y is. So for the slope field, not bad. I'm going to add 1 to it. So when y is equal to 0, the slope is going to be 1. I'm going to do a duplicate thing, I think. Try to speed this along. Go back and then duplicate. And then I didn't duplicate enough. So we'll go here. And then when y is 1, the slope is 2. You know, I don't know. Maybe it's faster to do this. This is too many points. Nobody should do this. So when y is 2, the slope is 3. It's hard to get a slope of 3. Like, you get a real appreciation for how steep things can be when you try to do this. And then just go parallel. Slope of 4, forget it. No way you're doing this accurately. This is so many more points than you would be required to do on like an AP exam, because like nobody's grading that. When y is -1, the slope is 0. That's good, which means that y equals -1 is a solution to this differential equation. And then the slopes will be kind of like a symmetric thing here. -1s, not bad. If not for that lunacy at the beginning, we'd be going really quickly through this. But you know, when the moon is full and you got to decide if something is concave up or down, you just go for it. You know what I mean? All right, we did that. Cool. Yay. Let y equals f of x be the particular solution to the differential equation with f of 0 equals 1. Cool. Step size of 0.1. Oh my God, 0.1. All right, so we got a table here. I want to change this to dy, and then I always want to remember it's f prime of xy and then delta x. So delta x is 0.1 because I was given. And we start at 0, 1. 0, 1. So then we're going to do 0.1. And then we just do 1 plus y. So you just add dy dx is 1 plus y. So the x value doesn't really matter. So to review, if the x value doesn't matter, then as x changes, as you move left and right, the slope's not going to change. And if you look, as you move left and right, the slope remains the same as you're moving left and right. Move up and down, the slope does change. That tells you that y is a part of the differential equation and x is not a part. So that's actually a really good review. So this is 1 plus 2. So we move that. You can fill in this whole thing initially. You don't really need to think that much about that because you just add delta x every time. So here we're going to add these to get this as 0.2. So we add these together to get 1.2. We're going to do 0.1. You have to add, you just use the y value, 1.2, which is like 0.12. This is going to get really annoying. There's a 1.32. We'll use a calculator to check this because I have no confidence in myself. 1.32. So this is 0.132. Kind of thought they would get smaller, but like whatever, you just go with it. So I have to add these. So it's 1.442. And luckily this is the last one. So 1.442, which is 0.1442. Then I have to add them. Oh good, 1.5862. So I think f of 0.4 is approximately 1.586. Well, 1.586. 3 decimals. Getting really dark. I don't know what's going on. So this is actually a differential equation we can solve before I use the calculator. dy dx equals 1 plus y. Let us solve that. So dy dx. Yeah, it's like I lost my, did I lose the ability to write? What is this? Okay, I don't know what's happening. I think it's probably crashed. And what happens when it crashes is it'll let me like do stuff for a while and then it's like, sorry. 1 plus y I'm going to write as y plus 1. I'm going to do times 1 because sometimes people are confused on how to separate this. We get this is equal to dx. You can actually use an integrating factor on this, by the way. If you subtract y and then do that, it's not really the intention, but it will work. So this is x plus c. So if you remember, we're skipping 2 steps. We're going to drop the absolute value and we're going to bring the constant down. Plenty of videos on that if you're interested. So -1 plus c e to the x. And then we know that the initial condition is like the given, so that's 0, 1. So let's use that. So 1 equals -1 plus c e to the 0. So c is equal to 2. C is like always 2. It's not. Don't get that idea, but like it feels like it is. So finally I get y equals -1 plus 2e to the x. So I can also plug in 0.4 there and see what we get. Okay, I'm gonna use a calculator to check this. Then obviously we're gonna end this because this has been a forever video. So what am I doing? I'm gonna use Euler. I'm gonna use the graph doc for 1 new problem graph Menu 3, differential equation. 1 plus y1. So it's 0, 1 again. It's always 0, 1. It's not always 0, 1, but it feels like it. Get to those dots. We got to change this to, we got to leave this at 0.1. Field resolution really doesn't matter. Like, it really doesn't matter unless you want to look at like a better picture. We want to trace this, start at 0. Actually, you just plug in 0.4, but let's see if we check along the way. 1.2, 1.42. Oh no. 1.42? Why is that? I got 1.32 and then it was all wrong. All wrong. What the heck? I did 0.1 times 1.2. Oh, I didn't add 1. Oh, I never added 1. Oh no. Oh my god, and this video is so long. This just, I'm not doing it again, so I'm gonna go back and fix that. I'm so sorry. Crud. Ugh. All right. How much of this is salvageable? Like basically nothing. These are wrong, these are wrong, these are wrong. It's all wrong. Crud. I mean, the 1's right, but like what good does that do us? So this should be 2.2 because you add, so it's 0.22, and then you add these and you get 1.42, and then 1.42. No, 2.42. Come on, brain. Ugh. 2.42 becomes 0.242, and then 1.662. 2.662 is 0.2662. Disaster. And then you have to like add and carry. I'm just gonna go back to the calculator and steal it. 1.99282. Ah, boy. It's a good thing we checked, I guess, but like so dispiriting. All right, that's what we get. Did it wrong. Man, you gotta watch out. You gotta let me know when I make those mistakes, except there's no way for you to do that. And then I'll just use differential equation solver, solve. Y prime equals 1 plus y, comma. Okay, so let's give it the initial condition. And y of 0 equals 1, comma x, comma y. We get this, which is what we found. And if I do this such that x equals 0.4, I get 1.98365. We got 1.928. Not bad. Not bad. Pretty close. I don't even think I'm sharing the right thing. What a disaster this whole video has been. But again, it's pretty long and I really don't want to redo it. So this is what I did here. I don't remember what I was showing you here. I don't know. Go back to the notes. We're done with this. I'm disgusted by this attempt. Here we go. All right, so it's finally right. I don't know, that's probably a 20-minute video that I shouldn't even have made, but it's done. So I'll see you in the next one where things probably couldn't go worse. So see you there.